Hi, I'm Katy from Estron Netherlands Institute for Space Research, soon to be at St Andrews, and I'm going to talk to you today about using a variety of different molecules in the retrieval of exoplanet atmospheres. So from what we know of the solar system planets and moons, and from what we expect from the many thousands of exoplanets now discovered, is for there to be a huge variety in the chemical makeup of exoplanet atmospheres. Some may adhere to equilibrium chemistry, where the metallicity and elemental abundance ratios can tell us the abundances of different species as a function of temperature and pressure. So others will have some more dynamic processes at play, such as strong winds, turbulence, or strong UV radiation from the star, and these will cause the chemistry to go away from this equilibrium. So in either case, having a detailed knowledge of what the spectra of many different molecular species looks like is essential if we want to have a complete as possible picture of what their atmospheres are made out of. So luckily, each spectra is unique and it acts like a barcode or fingerprint to tell us exactly what is in the atmospheres of these exoplanets. So in this talk, I will try and answer a few questions related to molecular spectra of various species. I won't have time to answer these all fully, but hopefully I can give an overview. So first is, how do we know what these molecular spectra look like? What are some of the challenges associated with finding this out? How do we use these in our exoplanet retrieval models? And what are some of the differences between molecular data which is used for either low or high resolution observations? So historically, these spectra would come from laboratory measurements taken here on Earth. And by far most commonly, these would be measured at room temperatures and pressures. And so these measurements or these spectra are typically only valid at the temperature and pressure of measurement. However, we know that many of the observed exoplanets, and in particular those which are easier to observe and therefore characterize, are those orbiting close to their host star, and therefore those which can reach very high temperatures in the parts of the atmosphere that we're observing. So luckily, there are some theoretical methods which we can use to work out what the molecular spectra look like for a given molecule up to high temperatures. So we use quantum chemistry, and we can use this to get a list of energy levels. And for a small molecule, which is around 3 to 5 atoms, these energy levels can number into the millions. And that sort of size of molecule is currently around the limit of our computational capabilities. We can also find the allowed transitions between these energy levels, and these can number up to billions. And we also get the coefficients which determine the probability of these transitions occurring. So they're called the Einstein A coefficients. And these later will give us the line strength, so the height of the nice absorption features that we see in our spectra. So there's a number of different groups who provide data suitable for characterizing these atmospheres up to high temperatures. One of the main ones is the ExoMol group at UCL, where I spent my PhD. And where they don't have data computed as part of their own project, they also host data from some of these other projects. So this list of energy levels, transitions, and Einstein A coefficients is called a line list. And in order to use these in exoplanet retrievals, we typically want to convert them to cross-sections. And these are pressure and temperature dependent spectra, where the line positions come from the transitions between different energy levels, and the line strengths come from the Einstein A coefficients and also the temperature. So I'll just give you a brief illustration of line broadening. So this is a stick spectra. So this is what you get before you take any broadening into account. So as I said, you can see the line positions. They're given by the transitions between different energy levels. And the strengths or the height of each of these lines comes from the Einstein A coefficients and the temperature. However, we know that spectra do not really look like this, and they're not straight lines, they have some shape. And there are a few different processes which cause this shape or this line broadening. So there's natural broadening due to the Pauli exclusion principle. There is temperature broadening. So this is due to the molecules moving around as they are absorbing or emitting between different energy levels. And so then there is a slight blue and red shift either side of the transition. And there's also pressure broadening, and this is actually due to other species which are colliding with the molecule which is doing the absorbing or emitting. So the spectra that we observe will be dominated by pressure and temperature broadening, so we often ignore the natural broadening. And this is just a note that the base component of an atmosphere will typically be what is known as the broadener. And in the case of hot Jupiter exoplanets, which are currently the most commonly characterized, then hydrogen and helium are the main broadeners. Okay, I think it's started again now.
Yeah.
Okay, well, there's all the line broadening definitions up here for you to read. But the spectra that we observe will be dominated by the pressure and temperature broadening. And so often we'll ignore the natural broadening process. And this is also just a note that the base component of an atmosphere will typically contain what is known as the broadener or the main broadener. And in the case of hot Jupiter exoplanets, which are currently probably the most commonly characterized, then hydrogen and helium are the main broadeners. Okay, so once we add this broadened profile to the lines, we'll start to see a spectra more like the ones that we're used to, like this. And to go from a line list to cross sections, I use a software package called ExoCross. And this directly works with XML format line lists and also those from HyTran or HyTemp. But there are other similar packages available which do very similar things. So together with some of the developers of 4 different retrieval codes, I recently led a project to compute these cross-sections in the specific format required for each code for all the molecules which we currently have molecular line list data available. So these retrieval codes are Arcus, Nemesis, Taurex, and Petit Red Trans. And I think some of you may have already learned about and even used this over the last few days. So for this database, I mentioned before that a spectra will depend on the type of species, which acts as the main line broadener. And so I should note that this database, XML-OP, is tailored specifically for characterizing hot Jupiter type exoplanets. And new cross-sections are required for exoplanets with different atmospheres. So for example, CO2, water or N2 dominated atmospheres. And there is active work ongoing in this area. So for this database, for each molecule, we computed cross-sections for 22 different pressures and 27 temperatures. So that's 594 temperature pressure points per species. going from 1 × 10⁻⁵ to 100 bar, and from 100 to 3,400 Kelvin. And this is just an example of some of the many species available as part of this database. So in total, including isotopologues, there's over 80 species. And some examples, more specific examples of available species include metal hydrides, such as these, chromium hydride, calcium hydride, iron hydride, and magnesium hydride. And these are used in classifying L-type brown dwarfs, amongst other things. And I think the first talk tomorrow, we'll hear more about that. So we also have some potential precursors to prebiotic species, such as those shown here: formaldehyde, hydrogen sulfide, hydrogen cyanide, ethylene, and acetylene. And the database also contains a number of ions. And we also heard about some of these earlier, H3+ in particular. And they've also been theorized in particular to have potential links with lightning chemistry on exoplanets. And I imagine also aurora. And finally, there's also a number of strong optical absorbers available. These are thought to cause temperature inversions in exoplanet atmospheres by heating the upper parts of the atmosphere, like some of these metal oxides. So this is just a quick note before I move on to quickly mention about K-tables. So I've spoken so far mainly about cross-sections, but K-tables are essentially a way of storing the opacity data contained in cross-sections in a cumulative way. And the advantage of this can be increased efficiency when using them in retrieval codes. And a few of the retrieval codes I mentioned in this talk use K-tables as opposed to cross-sections. And so I kind of use cross-sections as a more general term. So this is an example to illustrate the importance of temperature dependence. And here we have some model atmospheres which contain only acetylene or C2H2. And we either use the data computed from theory. So this is what I computed during my PhD, the EXOMOL data, or the HYTRAN data, which is based on room temperature lab measurements. So you can see at 300 Kelvin, there is not so much difference between the two. But when you go to 1,000 Kelvin, you can see that there's large gaps in the blue laboratory data. And it's essentially just extrapolated from the 300 Kelvin upwards. And so these gaps, this is mainly due to missing hot bands. So these are transitions between high energy levels, which weren't populated at room temperature. And while I'm talking about warnings, so apart from temperature, you also need to look out for wavelength region. So this table is taken from extract from a table in the EXOMOL OP database paper. So I've given the archive link here. And you can see that SIO has a minimum wavelength of 1.65 microns. And this corresponds to a maximum energy up to which the line list was computed. And so when you use this data in your retrieval or forward modeling code, it may seem like the opacity sort of suddenly drops off, but this is actually just an artifact of the data not being computed in this region, and it doesn't mean that there isn't opacity there. So actually for SIO, there is now a new line list being published soon, which will extend all the way down to the UV. So before I move on, I'll just summarize what I've spoken about so far. So in general, laboratory data, which is provided by large databases such as HYTRAN, is accurate, but largely only suitable for characterizing atmospheres that are room temperature. And theoretical data is typically valid up to higher temperatures, but it can be very computationally intensive to compute. And you need to check for each species what the maximum recommended temperature and also the valid wavelength region is. So before I go on to talk about some examples of retrievals which use this data, and then about the different data suitable for high resolution observations, this is just a quick note on how to access all this data that was computed for the ExoMol OP database. It is available on the ExoMol website, and you can search by going to data, data type, opacity, and then click on the species that you're interested in. If you scroll to the end, you'll see that the data is available to download in the format of the 4 different retrieval codes, which I mentioned previously. So Nemesis, Taurex, Arcus, and Petit Red Trans. And the reference to the original line list used is also listed below this data. Please do cite this in your work, in particular if you make a detection, if you do use this data. And not only is it nice to cite people's work, but it's also important because the line lists are updated periodically. And so it's important to mention which version you're using for a particular species. And if you click through to these references, they will also tell you information on the temperature and wavelength region that the line list is valid. So after computing all these cross sections for use in retrieval codes, I then led a project where we reanalyzed some archive Hubble HST transmission spectra of WASP-43b. So WASP-43b is a hot Jupiter exoplanet orbiting close to its host star, and it's assumed to be tidally locked, so the same face of the planet is always facing the star. This is the transmission spectra that we used from Kreiberg et al. 2014. So you can see the data points with error bars, and then in blue is the best fit retrieval model, which finds some evidence for water vapor based on this absorption feature here. So we did a systematic retrieval analysis using both the Arcus and Taurex retrieval codes, which uses all the data currently available of different molecular species which have absorption features in this wavelength region of the WFC3 instrument. So that's around 1.1 to 1.7 microns. So when we only included a handful of species, we also found evidence for water vapor. And this was our best fit retrieval for that. But when we looked through all the other species, we found that there was some evidence to suggest that aluminium oxide, or ALO, could also be present in the atmosphere as well as H2O. So you can see here that the absorption features seem to fit the data quite nicely when ALO is also included. I should also note that the line list for ALO and also for some of the other species were not available at the time of the original observation in 2014, which is why a reanalysis can help find any evidence for different species in the observed data. So I was also part of a team led by Marek Bram, who is now a PhD student at Edinburgh University. So he led a similar systematic retrieval analysis, this time of WASP-31b, Hubble transmission spectra. And this extends down into the visible using the Taurex retrieval code. And again, using a systematic analysis to search for any species with absorption features in this region, we found that there was some evidence for chromium hydride. However, for both this study and the last one, these are really only hints that these species could be present in these atmospheres. And in order to confirm and to place tighter constraints on their abundances, we really need data observed over a wider wavelength region, and ideally also complementary high-resolution observations, which are typically taken using ground-based telescopes. So with this in mind, I'll move on to talk a little bit about data, which is suitable for characterizing atmospheres which have been measured in high resolution, for example, using the cross-correlation technique, which you have heard something about, and I think we'll also hear more about over the next few days. So this image is the VLT, contains the recently upgraded CryoRes Plus instrument, which will have the correct wavelength region of around 1 to 5 microns to be able to observe the spectra of many different species with available lineless data, so such as those that I showed earlier. However, these lineless used for high resolution observations, such as these, need to have very accurate line positions. So this was not so important for the low resolution observations, which I just showed, where the completeness of the line list was far more important. And so for all the 80+ line lists, which I mentioned before, these need to be upgraded to make them suitable for characterizing exoplanet atmospheres using high resolution observations. So for this, we use the high accuracy laboratory data, which has been measured at room temperature, to make our theoretical line lists more accurate. And we use a procedure called MARVEL, which stands for Measured Active Rotational Vibrational Energy Levels. And for a particular species, we will collate all the laboratory measurements in the literature, which can span decades, and analyze them to get experimentally determined energy levels. So I've been involved in a few of these projects, and the first was a few years ago during my PhD for acetylene, or C2H2, which is the molecule which I computed the lineless for. So I led a small team working on this, and together we gathered almost 38,000 experimental transitions from 61 different publications, and we analyzed them using MARVEL to get over 11,000 experimentally determined energy levels. So we can then replace the energy levels in our theoretically calculated line list with these more accurate ones, and it will shift all the lines around connected to those energy levels to get a far more accurate spectra. And in reality, it won't be as nice as the one I've shown illustrated here. All the lines will be moved by different amounts and in different directions. But once we have this new, more accurate line list, we can use it to compute cross-sections, which can then be used, or they're suitable for use in characterizing atmospheres using the cross-correlation technique. So this work for acetylene was done as part of an initiative called ORBITS. This stands for Original Research by Young Twinkle Students. And in ORBITS, a PhD student or a postdoc is matched together with a group of 6 to 12 high school students, so aged between 16 to 18 years of age. And together they will work on an original research project, which is related to the spectroscopy of exoplanets. And you can see the publication here that was published a few years ago now. It has 6 of the co-authors with their address listed as a school in North London. So very excitingly, last year, this data was used in a high resolution cross-correlation study where 6 molecules were detected simultaneously in a hot Jupiter type exoplanet, HD 209458b, And this included the first detection of acetylene in an exoplanet atmosphere. So the other species detected were H2O, methane, ammonia, acetylene, hydrogen cyanide, and carbon monoxide. And as a result of these detections, the planet is now thought to be carbon rich. And this has some connections and implications for things such as planetary formation history. So I mentioned before that XMOR OP was only suitable for low resolution retrieval studies, and that only some line lists are currently suitable for high resolution studies, although this is an area which is actively being worked on. And a few of these line lists have been used to compute high resolution cross sections, and these have been made available online. So you can see, for example, this publication from last year. So before I finish, I'd like to briefly summarize the answers to the 4 questions, which I highlighted at the start. So firstly, how do we know what these molecular spectra look like? So this is really from a combination of laboratory experiments and theoretical quantum methods, and these are complementary. What are some of the challenges associated with this? So both the lab and the theory are challenging at high temperatures. Computing a line list for one species can take years. It's very computationally intensive, particularly for molecules with more atoms or electrons. And I didn't go into this, but also there are other complexities associated with certain species, such as interacting states. So that might be why, if you want to know what a particular species looks like, it might not be currently available. How do we use these in our exoplanet retrieval models? So for low resolution observations, there are databases such as XMOR OP. This is the one I concentrated on because obviously it's the one I was involved in, but there are some others available. So this one was particularly formatted for these 4 different retrieval codes: PuTTY RedTrans, ARCIS, Taurex, and Nemesis. And for high resolution, so cross-correlation studies, only some line lists are currently suitable, and this is actively being worked on. And there are also some high-resolution cross-sections available, e.g. see Gandhi et al. 2020. And finally, what are some of the differences between low and high-resolution data? So apart from what I've just mentioned, it's important to remember, so completeness is more important for low-resolution studies, but accuracy is generally most important for high resolution. Obviously, a combination of the two is ideal, but please check that a line list is suitable for high resolution in particular before using it. So there's just one final message that I'd like to leave you with now. So that is that, in my view, there are really 3 main ingredients to retrievals of exoplanet atmospheres. The first is observations from high-tech instruments. So these are both space and ground-based. And also there is lots of theory involved in formatting these observed spectra in a nice way. The second is suitable molecular data for all of the different species which could be present. And this is what I've concentrated on mainly in this talk. And third is a suitable code and all the theory which comes along with it, which uses these other 2 components as input in order to extract information from the atmosphere. So these codes are typically tailored for either low or high resolution observations, sometimes both. And there is ongoing work in all 3 of these fields, which is very exciting, and I hope means that we'll be seeing many more publications related to observations of lots of different molecules in exoplanet atmospheres in the years to come. thank you for listening. I'll leave up the links for the XML OP paper and database. And I'm happy to answer any questions now, and also feel free to contact me later. Thank you.
Thanks, Katie. That was a really great overview. Do you have any questions, either if you want to type in the chat, or maybe it's easier if you just raise your hand?
I think I see a hand raised.
I can't see one, but if you have raised your hand, feel free to just unmute yourself.
Is it Eleonora, or was that accident?
No, I was actually clapping, but yeah.
Oh, okay.
Sure, but great talk, by the way. I have many questions, as you know, because we've been in touch quite a lot about the lines, so I don't really want to monopolize the whole conversation, but I will shoot you an email no matter what.
Sure, thanks.
Cool. I mean, we have about 8 minutes or so before the next talk, so we could get a sort of discussion going if we have more detailed questions. Okay, so, well, I was wondering, you often talk about or we hear a lot about the accuracy of the line positions, which of course is important for cross correlations. I'm just wondering how accurate the strengths of the lines are, if we know that for as we move to these high resolution retrievals that we talked about earlier in the week.
Yeah, that's actually a really good question, because that is something that's come up with people who do the cross correlation observation characterization. It depends on the species. So, and it's the kind of thing where originally we were focusing on the line positions, and then we found, I think it's particularly titanium oxide, maybe vanadium oxide as well, that potentially there could be some issues with the line strengths, which for the cross correlation, I think has some implications on how, like, the signal strength, I think it is.
Yeah, I was also wondering, yeah. Does it affect your confidence?
Yeah. So the answer is yes. And so that feedback has kind of led the people doing the theory on that to go back and relook at the line strengths. And so also using the lab measurements for that as well.
Right. I mean, is there a good way to check how accurate it is if you can't do the lab measurements, if it's really high temperature?
Well, so it's kind of similar to what we do with the line positions, is that we can look at the lab measurements at room temperature and look at the line strengths. And then we look at our theory at room temperature, and we can see if we match the lab strengths. Again, it varies on molecules, how good the lab data is and how much work has gone into it. So then again, that's a feedback, and then the lab people will go in. So it's there's an interlink between lots of fields, which kind of helps push this data forwards.
Cool, thanks. Okay, any other questions? Yeah, if not, we can also use the Slack. Don't forget to check that after, or often if students have questions much later, they can post them in there.
Yeah, definitely.
Okay, cool. Well, in that case, we can move on to Aurelien.
Thank you.
Thanks very much, Katie.
Hello.
Aurelien was here. Yes. Hi. Okay, do you want to share your screen?
Yeah.
Okay, great.
So
yes, we can see. So this is.
You see the mouse too? I'm just curious.
We see the mouse. Yeah. Great. So this is Aurelien Falco from Laboratoire d'Astrophysique in Bordeaux, and he's talking about transmission spectra of multidimensional atmospheric simulations.
Okay. So I will just start with a bit of context on what we are trying to do here. So obviously the goal is to compute transmission spectra. But the idea is that we have GCM simulations. Like this one is WASP 121b. And so we wonder how to compute the intersection of the rays of light with this simulation. So the usual approximation, let's say, nowadays is to use a 1D approximation, because obviously it's much faster than a full 3D model. And so it can be used, for example, in the context of retrievals. The only problem is that, well, as we've said before, planets are not 3D. Planets are 3D, so for a 1D approximation, there could be some biases, and this is especially the case, as been shown by William Curiel on ultra-hot Jupiters. So with the full 3D model, we are also capable of generating transmission spectra. But the problem is that this 3D model, which has a more realistic structure, is a bit too slow for retrievals, at least in 2020. So what we proposed is to use a 2D model, which is in between the two, which is fast enough so that we can use them for retrievals, but which is a bit more precise than the 1D model, and which can take into account the difference of temperatures between the day and the night in the context of ultra-hot Jupiters. This 2D model has been implemented in the Thorax framework so that we can effectively compute retrievals, while the 3D model is a standalone code which is called Atmosphere. I will come back to that later. So just 2 words on the 2D model. Since we are going to use them for retrievals, we don't define the temperature, for example, in each cell of the model. We use a limited number of parameters. We set a temperature on the day side, a temperature on the night side, and then we compute a linear transition between the two within a specific angle beta that can also be retrieved. Plus, there will be a deep layer, which is isothermal. So to compute the optical depth in this grid, since the input grid is given in pressure levels, we interpolate the data into a spherical grid in which it's much easier to compute the optical depth. We just have to compute the intersection of these rays with it's a just geometric formula, let's say. So once we have computed the optical depth, we are able to generate a transmission spectrum. So we are talking here about 3 models: 1D, 2D, and 3D. And for the rest of this talk, I will present 3 test cases in which we can study how they behave. So first of all, we will see how they will behave in an isothermal atmosphere, in which we can compute all 3 models. Then we will move on to a bit more complex problem, which is 2D, in which we can compare the 2D and 3D models. And we'll talk about that a bit more later. Then we'll discuss a bit more about how to compute what we can do with a 3D model using a GCM. So in the isothermal case, we set a pretty high temperature to see, let's say, a big effect on the spectral variations. So here we have a convergence plot for all three models. We have T stands for thorax and P for atmosphere. And the number is the dimension of the model, of which we increase the number of layers. And we study the mean of the absolute difference between this model and the converged model of atmosphere. So for example, for almost every model here, if we want to reach an average of 1 ppm of difference, we need approximately 200 or 300 layers in the models. You may notice that thorax, the implementation of thorax, the original implementation is a bit slower to converge. And that seems to be due to the fact that they place the rays to cross the layers at the bottom of each layer at the terminator. So by just shifting a bit the rays, we can reach actually much faster convergence, meaning that we need less layers to have the same precision. Okay, so that's for the isothermal example. Now we can move on to a 2D example, which is trying to replicate actually West Point 1b. So we have a very hot day side and a colder night side. In this case, we can also study the convergence of the models by increasing the number of layers. But this time we have also the angular dimension. So we can study also how do they behave for specific angular resolution. So we have here the 2D code and the 3D code. If you look at a similar angular resolution of 1 degree in purple, you can see that actually the two implementations have a pretty similar trend, which is just a validation of our models. Since we encoded them in a similar manner, they obviously have the same behavior. And what this plot tells us is that we also need a few hundreds of layers to reach a ppm level with an angular resolution of less than half a degree, let's say. So since our goal for the 2D model is to run retrievals, this slide is a bit complex. I will just focus on the results. We studied the performance of the 1D and 2D models to see if it's, well, let's say, feasible to run 2D retrievals. So the conclusion of this study was that basically, for a pretty high accuracy, the 2D model will be 10 times slower than the 1D model. So obviously it's a bit slower, but it's still within a human time scale, let's say. So currently we are able to do 2D retrievals. This talk is not about retrievals, so I will just show one example, which is here for West Point 1b. We have a 3D simulation that looks like this, of which we have computed the transmission spectrum using atmosphere in 3D. And we are trying to see what the 2D model will retrieve. So we have a lot of parameters, but we have a H2O, CO, TiO, and VO here. But most importantly, what we can see is just that it's reaching, let's say, a satisfying set of parameters, which is close to the original simulation. So for the last section of this talk, I will move on to a 3D example in which obviously, well, the 2D model cannot replicate these effects. So we take the example of WASP-121b, and in the 3D model, we have a new information that we didn't have in 1 and 2D. On the right, we have here a transmittance map. So that's the opacity of the planet, let's say, seen from the observer. In 1D and 2D, we will have only one angle here of information. When in 3D, we have this whole new dimension, angular dimension to study. So that's just another convergence plot in 3D to see where we can reach the ppm level. But what is interesting with this transmittance map, and I will show it in a study case here, is that we can study, for example, east-west effects, east-west characteristics of the planet. So to show what I mean, we study here, in the case of WESP 1b, the rotation of the planet. Well, we assume that the planet is tidally locked, so it's always showing the same face to the star. So we can just change a bit the position of the observer to see what effects it has on the transmittance map. So for this specific time of the transit, I've shown here the transmittance maps associated with these steps of the transit. And once we have this transmittance map, therefore we can integrate them to have a transmission spectrum. What we will do here is that for the ingress and egress, we will only select the transmittance that is in front of the star. Basically, we'll just ignore the part of the planet that is outside the star. And we normalize it so that we can compare the transmission spectra. So we can produce something like this. We have here the transmission spectra for this specific phases of the transit, with their differences to the mid-transit here at the bottom. And well, the immediate thing that you can see on this plot is that there is a huge bump at the egress, which is due to the fact that the east limb here is much larger actually than the west limb. So if, of course, we select only the transmittance map that is in the star, we will have a sort of effect of doubling the atmosphere. So this is due to the simulation, of which we have a temperature map here on the right, which is not exactly symmetrical. What you can see here is that at the longitude 0 is at the substellar point. What you can see is that the hottest temperatures on the simulation are actually a bit shifted to the east. So if you have very sharp eyes, you can check that actually the atmosphere here is a bit larger than on the right, but it's take my word for it. So this is actually visible in the transmittance map. This east limb is always a bit larger than the west limb. The only thing is that when we move to the ingress, the hottest part of the atmosphere is moving behind the planet. So it's kind of averaging out the transmittance, and we get a more normal radius. While for the egress, the hot temperatures are moving very close to the west limb. And so it's giving this impression that the east limb is very much larger than the west limb. So that's one example of what we can do with the 3D model, including changing the position of the observer. So as a conclusion, we had 3 models that we presented in this talk, of which the 2D model can be used for retrievals. But it's not enough to study 3D problematics, let's say, in which case we need a full 3D model, which is a atmosphere, with which we can, for example, study the rotation of the planet. So we'll just leave you a link to this code. Just be warned that we are actually working on a new release in which maybe there will be some emission and there will be maybe some new things. So that's the online version is a bit old, let's say, for now. It's 6 months old. And with that, well, I will end my talk. Thank you for your attention.
Great, thanks, Aurelien. That was very good. We already have a question in the chat from Ryan. He said, for the 2D retrieval of WASP121b, what did you assume about the data? Number of transits, wavelength range, etc.
Well, I didn't want to dwell too much on retrievals. I guess there should be 30,000 wavelengths. I don't have the spectra, actually, the input spectrum generated by Atmosphere. But what was I don't remember what you said about the characteristics. Which characteristics you wanted to know about?
Number of transits, wavelength range, etc.
But yeah, so the wavelength range, I guess it's approximately 0.5 microns to 15 microns. And yeah, we are always assuming that we are at mid-transit, so we are yeah, in the middle of the transit. I don't know if I fully answered the question, but
yeah, I mean, Ryan, you can also unmute if you want to discuss further. Yeah, Julia also has a question.
If the one before is done, then I'll go ahead. So I have actually 2 questions, if that's okay. Thanks for the talk. I'm always very curious about what the theorists are doing on the simulation side. So my first question is, again, I'm torturing you with the data. So we've seen quite often in the data that we have a broadening of some features that can either come from a temperature gradient that is quite strong or from winds. And I'm wondering, first of all, the temperature gradient seems quite strong in what we see in this 2D retrieval. And I'm wondering if you're also considering to include 2 or 3 dimensional winds in your models to really get this degeneracy between these two physical properties properly.
Actually, yeah, we are looking into that. So we wanted to check about the winds. It's not implemented yet, but it's something we are looking at indeed.
Cool. And then the second one is actually a little bit of a specialist question. So what do you code this in? And do you use also do you run it on a server on your local machine with a graphics card? And do you use pure Python with Numba, or do you use Julia? And what do you do?
It's mainly Numba, actually, with a bit, I think we have a bit of C code in like extensions, but not much. So it's mainly Numba. And we are running on a cluster, a local cluster, which we are not really running for the retrieval. Obviously, we are running in parallel, but for the 3D code, for example, we are just running in sequential.
Okay, cool. Thanks.
Cool. We have about 5 minutes till the next talk is supposed to start. So there's another question in the chat from Evet. He says, do we really need the 2D retrievals to infer some of these 3D properties, or would 1D retrievals on different parts of the transit be enough to infer some of the temperature differences and asymmetry?
Well, that I don't know about how to infer characteristics with different steps of the transit in 1D. I'm not sure what it will give you as information. But that in any case, it's more the the subject of these papers that show the biases of the 1D models. I guess they didn't study actually 1D models at multiple steps of the transit. So I don't know about this.
Even something like using a different model for the east and west limb of
yeah, that would be actually interesting to see. We didn't do this comparison, so that's definitely something we should check, like how much information we can derive from a 1D model with east-west effects. And
thanks.
Cool. Ryan has a raised hand.
Yeah, just another follow-up question. Could you go back to the column plot for a moment?
For which one?
For the 2D retrieval, please.
Sorry.
Yeah, there we are. So yeah, so I noticed from that you only have one free parameter for each of the abundances. So presumably you're assuming a uniform abundance, things like H2O, between the day side and the night side.
No, actually we have so we are assuming a deep abundance, but in this case we are using a module from Vivien Parmentier that is computing a dissociation. And so for example, H2O is absent from the day side because it's too hot.
Okay, yeah, that's what I was going to ask. So why are you assuming that you know a priori exactly how much the dissociation would be, instead of, for example, having a free parameterization of the separate abundances on the day side and the night side? Thanks.
Well, we studied a bit these retrievals with dissociated parameters for each species. If you put the parameter on the day and on the night side for each species. But somehow the model was behaving there was weird effects, like it was trying to put, for example, H2 just on one side and nothing on the other side. So I don't know. It looks like for now this is the model that is working the best, that is the most stable. It's just at least it's an option.
If we're going to talk about the retrieval, I've got another question, unless, Ryan, you want to continue?
No, that's all right. Please go ahead.
All right. So my question, with your input model here, do you have clouds in it, basically? Because it looks like when you retrieve it, you don't retrieve clouds on either the day or the night side. And that seems...
No, I find not seeing any... There should not be any clouds.
Okay. All I wanted.
Great. Are there any other questions in the last minute, or if not, we can move on. Thank you, Aurelien. So next up we have Yassin Jaziri.
Yes, hi.
Yes, hi. You can share your screen. Great. Oh.
Okay, is it okay?
Yep, that looks good.
Perfect.
Okay, so yeah, this is Yassin Jaziri, also from Bordeaux. Is that correct? Yeah. And his talk about developing a 3D generic photochemical climate model.
Yes, indeed. So hi. So I'm going to present some photochemical development on a 3D generic atmospheric model, and then an application with transmission spectroscopy. So the first part will quickly highlight the technical development, while the second part will show an application of an Earth atmosphere around a red dwarf, and in particular the ozone observability and the ozone observability by transmission spectroscopy. So the atmospheric model is a 3D generic global climate model, which is designed to simulate the diversity of atmosphere, considering the diversity of exoplanets we can find. And here we will focus in particular in the chemical reactions related to the stellar radiation happening in the atmosphere, what we call the photochemical processes. So first, we implement, the first implementation was to adapt a generic read for the diversity of chemical networks, which have been tested with an Earth, an early Earth and a warm Neptune network. But the crucial development was to implement non-line calculation of the photochemical rates and the photochemical heating tendency, which cannot be done in a generic way with pre-calculated lookup tables as it was done before. And one of the challenges to do that was to be careful about coupling the different radiative transfer methods into the GCM, because, for instance, the photochemistry use cross sections, while the general radiative transfer use correlated K tables to speed up the GCM. And to deal with the diversity of resolution and composition we can find to compute the correlated K tables, we use the Python library ExoK. So we validate all the development with the NERSC application by checking the temperature and the ozone profile, which are very good indicators for the photochemistry and the photochemical heating of what we developed. And so here you can see the GCM output and the data references for Earth. And you can see that we get a good agreement, and in particular for a generic model, which is not overtuned for the Earth. So when we did that, now we can move from Earth to exoplanets, and in particular, exoplanets around a red dwarf. So we applied the atmospheric model for an Earth atmosphere around the TRAPPIST-1 red dwarf. Why is the TRAPPIST-1? Because it has been found 7 Earth-like planets, and in particular, the TRAPPIST-1e planet is more likely to be habitable. That's why we focus on this one. And here you can see the stellar flux received by the Earth in blue, and the one received by TRAPPIST-1e in orange. And what showed up is that we have a huge difference on the spectral distribution, and in particular between the UV and visible balance is not the same at all. So to move from the Earth to TRAPPIST-1e, we modified the input spectra, but we also set up different parameters, as the obliquity has been set up to 0. And probably the more important, we tidally locked the planet, meaning that we have a permanent day and night side. So one side with photochemistry and the other side without photochemistry. And the results for ozone and the temperature show that we can sustain on those conditions an ozone layer 1 order of magnitude more abundant on TRAPPIST-1e than Earth, which is represented here by the orange line for the TRAPPIST-1e simulation compared to the Earth simulations. And we can explain that looking at the spectral distribution. And in particular, if we have a look of the cross-section, we can see that below 200 nanometers, we produce ozone by photolyzing the oxygen. And above 200 nanometers, we destroy the ozone by photolyzing the ozone. And with this new spectral distribution in TROPISS 1e, we see that we increase the production and ozone and we decrease the destruction of ozone, both going the same way with a higher production of ozone. And that's why the new equilibrium state is present more ozone. So this is in average, but we have a 3D atmosphere, and we can have a look of the distribution of ozone on this atmosphere. So if first we see the longitudinal distribution of ozone, we can see that the ozone layer is pretty much homogeneous over the planet. And even if on the night side, we do not have photochemistry. Because we are in a fast rotator regime, we have actually a good mixing, and that explains that at those levels, the ozone layer still remain homogeneous on both sides. But what we will observe will mainly what's actually it's interesting for the transmission spectroscopy. It's more to focus on the limb profiles. So that's why here I show you the west limb and the east limb, and you see that we have a latitudinal variation, but with a bit less ozone at the pole. But actually, it remains very tiny variation compared to the vertical variation of the ozone. And that's why we can say that we have only significant vertical variation of the around the limb. So this is very important for what's coming next when you want to analyze the transmission spectra you can get from observation. And what we do with all this 3D structure we compute with the GCM is now we can compute theoretical transmission spectra thanks to the PyAtmosphere code, which take into account the whole 3D geometry of the planet, and that's what you can see here. The computed transmission spectra of the planet with some different contribution of the main species which are highlighted, water vapor, CO2, methane, and in particular the 5 and 10 micron band of ozone. And now we computed the transmission spectra. The idea is to know if we can retrieve the molecules and if we can observe it. So first, for the retrieval, which is a 1D retrieval using the Torex code, we first compute a needleistic low photonoise uncertainty, just to see if we can retrieve what we have in our planet. And I show here four retrievals where either I considered an isothermal or 4-point model for the temperature, and either if I'm using a constant or a 2-layer model for the species retrieval. And what we can see is that, for instance, if we zoom on this wavelength, you can see that the 2-layer retrieval in dashed line can retrieve the spectra, and and the spectra is not well retrieved without this with a constant profile retrieval, and in particular here in the water band, but also at the other wavelengths of the water, and in particular at the 5 and 10 micron bands of ozone. And that is because it is the two main molecules which have high vertical variations. And the conclusion is that without multi-layer model, if you have a strong vertical variation, you cannot well retrieve your spectra. And it induces biases if you use only 1D retrievals. And indeed, if we have a look of the in solid lines, you have the retrieval profiles of the different species compared to in dashed line the model. And you can see that with the two-layer models, we get a good agreement of the retrieval. So that's for the retrieval part. And now if we want to have a look of the observability of this feature, because we saw that we have like 1 order of magnitude more ozone, so is it detectable or not? If we do a test with a GWST and we use the PandExo tool to compute a more realistic noise, as you can see in dot blue, you have the noisy spectra computed for 10, 30, 50, and 100 transits. And in gray, you see that we can retrieve with Torex, we have a retrieved spectra. But the question is it significantly retrieved because it's very noisy? So does it mean something? Does it mean that we can be confident for ozone detection, for instance? And if we have a look of the result of the retrieval, we can see, for instance, that for 10 transits, we do not constrain all the molecules, so it cannot be relevant to say like, okay, this is a good retrieval. But for 30, 50, and 100 transits, we constrain the molecules, but we need a criteria to say like, okay, it means something or not, and that's why we use a bias factor, what we call the ADI, and here the delta O3. And so the ADI compare a retrieval model to a flat model, saying like that the molecule you put to retrieve means something, or it's just like if you have only a cloud model. And what is interesting for us here is more what we call the delta O3, which compares the full retrieval model to a retrieval model without ozone, and to see if the detection of ozone is significant or not. And so we use the Beneke and Seeger criteria, saying like for the bias factor more than 5, you can say that it's a good detection. And so here, for what we've done, a good detection for 50 and 100 transits, meaning that it's still a challenge to detect ozone on such planets. So finally, what I showed here is a full procedure which can be applied to different atmospheres, molecules, range of wavelengths, and even different telescopes, starting to an atmospheric simulations, followed by transmission spectra simulations, all done in 3D, taking into account the complexity of an atmosphere, and then until a 1D retrieval model. And this is very important for the synergy with the observations to better understand what we get and characterize observability and to choose the better targets. Thank you very much.
Great, thank you so much. Very interesting. Do we have questions? Yes, Brian has raised his hand.
Hello, could you go back to the slide with the simulated James Webb data for a moment?
Oh, this one.
Yeah. So it looks like there's a combination of NIRSpec Prism and MIRI LRS data there. So could you clarify when you said 50 transits, for example, is that 50 transits with both of the instrument modes individually or 25 of each?
No, it's 50 transits for the two instruments.
Okay, so 50 transits is 100 in total. That's just what I wanted to check.
Yeah.
Great, thanks.
I guess you can't use them simultaneously. Any other questions? Yeah, Gabriella.
Hello, everybody. Thank you, Yassin. Very nice job. Very nice talk. Could you, maybe you mentioned at the beginning, but I probably missed it. Could you give some more details on the photochemical model that you have included? I mean, how many molecules, how many chemical reactions, and do you plan to extend it to more molecules? Could you just explain it a little bit more in detail?
Yeah. Actually, here it's based on a NERSC network. So the module take into account around maybe between 100, 150. It's a reduced network used for GCM. So I have around maybe 15, 20 photochemical reaction and around 150 reactions maybe. Yes, I forgot. What's the other questions?
Yeah, the other question was the molecules. How many molecules?
It's around. It's actually exactly 29 species.
Okay, so that's enough. Yeah, I thought it was more reduced. Yeah.
Yeah.
Congratulations. Then yeah, I'm curious to know. Maybe you can send me the list, and yeah, we will collaborate for sure in the future. I would like to know if it's already available for other GCM users, or we have to wait your PhD defense first.
No, I guess the network is based on usually well, it's already used on other for other studies. So no, it's not a problem to have the network.
Okay,
now.
excellent. Thank you very much.
Great. And another question from Michael.
Yes, maybe in the same vein. So the ozone production network here. I may also have missed it, so I understand. Okay, so it's a network of 29 species that you believe are probably at the right level of abundance in this atmosphere for this TRAPPIST-1e. But I mean, how sensitive is it? How has this been verified? How sure can you really be that ozone at this level is produced and is in equilibrium? Wouldn't, I mean, so I'm just wondering how safe it is to assume that this model is true and predicting the right amounts of ozone.
Actually, it's a very specific case. I mean, we know how to reduce all the complex chemical reaction we can have to model the Earth, and so we verified that we can reproduce the Earth, and now we took the same network and the same atmosphere, and we just changed some parameters, and the key parameter here is the input spectra, and
yeah, but now I'm completely confused. So in the case of the Earth, the main chain in producing ozone is through oxygen, O2.
Yes.
So have you assumed that you have these amounts of oxygen in 1e?
Exactly.
Yeah, but okay.
It's totally
okay. So it's an Earth-type atmosphere that you're assuming.
Exactly. It's just the Earth's atmosphere, and we check how the irradiation of the TRAPPIST-1 spectra.
Then I got it. I somehow missed the oxygen then in all your spectra, because the oxygen would also show up.
Yeah, no, it's totally a theoretical case. I mean, it's not true at all. We can't have this amount of oxygen and such atmosphere in TRAPPIST-1e.
No, thank you. That's very helpful. And I think that's of course, one approach. You have to start somewhere. So you start with the Earth atmosphere. So
exactly.
Yeah, good. Thanks.
Okay, thank you. Yeah, if anyone has any other questions or for any of the speakers today, we can use the Slack channel. Now we have a short 20-minute tea break and we reconvene at 5:20 European time. So see you then.